So good morning. Welcome to the next lecture of Signals and System. The lecture is Signal Transformation, Part 2. Since in the last lecture we had studied two signal transformations, time shifting, time reversal. Today we are going to focus on time scaling. So what do we understand by signal transformation? Signal transformation is nothing but we are going to do certain operations on the signal, right? And those operations are shifting, reversal and scaling. And there's a word associated with all these operations, which is time. What is the meaning of this? The meaning of this is all these operations, shifting, reversal and scaling, are going to work on the time axis of the signal. So that should be very, very clear. So shifting, what we understood in the last lecture, shifting, we are going to shift the signal with respect to time. It means that either we are going to shift the signal to the left hand side or to the right hand side from the current position. What do we understand by reversal? Reversal means we are going to take a mirror image of the signal along the y-axis, right? So if the signal is on the left hand side, when you take the reversal of it, the signal is going to appear on the right hand side and vice versa, right? So you're going to fold the signal along the y-axis. This is called as time reversal. So we have already completed shifting and reversal in the last lecture. Now we'll move to the next, that is time scaling, right? So what do we understand by the word scaling? So scaling means we are going to either increase the time axis or we are either going to decrease the time axis. That is the meaning of the word scaling. Right? How do we do that? How are we going to increase the time axis or either going to decrease the time axis? So let us see how time scaling actually works. So time scaling is done by multiplying a constant to the time axis. So if I say the constant is A, let me choose a constant as A. And if I now have a signal xt and I multiply the time axis by A, the resultant signal is x of at, right? I have done the time scaling. Either the signal may be x of at or x of t by A, right? Both of them result in a time scaling operation because you are changing the scale of the axis, right? So this is called as time scaling. If I talk on the similar lines with dt signals and if I consider a as my scaling factor, right, then x of an or x of n by a results into scaling of the signal, right? So scaling is simply done by multiplying a constant to the time axis. So maybe it's a CT signal or a DT signal. The multiplying with a constant a to the time axis results in time scaling operation, right? So time scaling changes the time scale of the signal. Magnitude of the signal doesn't change. This is very, very important, friends, that magnitude doesn't change. What changes is the time. Magnitude remains the same, right? This is very, very essential for you to understand, that we are not going to disturb the magnitude or the amplitude of the signal. What is going to change is the time, right? Let us understand this with proper visualization of the signals. Okay. Now, there are two types of time scaling operations. One is signal compression and another is signal expansion. If your scaling factor A is greater than 1, right, time scaling results in signal compression. Right, so A greater than 1 means what are the values A can take? The constant A can take values like 2, 3, 4, 5 and up to infinity. Right, so for example, if my A is 2, how is the signal is? The signal becomes x of 2t. If my A is 3, the signal will be x of 3t, x of 4t and so on. Right, so if my A values are greater than 1, it results in compression of CT signals, right? I'm talking about CT signal here. If I talk about DT signal and if my A values are greater than 1, the resultant signals will be x of 2n, x of 3n, x of 4n right? And all these operations results in compression of the DT signal. Similarly, if I take another case in which I'll put a value, I will choose the a value to be between 0 to 1. In that case, what is the time scaling? Time scaling results in signal expansion. It results in expansion of the signal. So for example, if a value is 1 by 2, the signal will be x of t by 2. If a value is 1 by 3, signal will be x of t by 3 and so on. So if we do such operations on the signal, it results into expansion of CT signals. Similarly, if I talk about DT signal and if I choose a value to be 1 by 2 or a value to be 1 by 3, the signal will be x of n by 2, x of n by 3, x of n by 4. All these operations, if you do on the DT signal, all these operations results in expansion of DT signal. How is it so? Because we just saw that time scaling is either increasing the time scale of the signal or decreasing the time scale. So if I increase the time scale, definitely it's going to be expansion. The signal will be in the form of an expanded signal. In other way, if I decrease the time scale, what it should result into, signal should be like signal as a compressed signal, right? So how these are actually resulting into compression and expansion, let us look at with certain example. So friends, here we are going to look at examples of time scaling operation. So I've taken a signal CT signal XT, right? The signal exists from 1 to 3 and everywhere else it is 0. So this is a simple CT signal we have taken, and what operation we are going to do on this? We are going to do the operation of scaling of the signal. So I am going to find x of 2t, right? So what is my a value here? My a value is 2, right? So I'm going to scale this particular signal by taking the a value as 2, right? What do we know? That this is going to be, if a is greater than 1, it's going to result into signal compression. So how is it? How is it going to land into signal compression is what we'll understand, right? So for that, before we look at this how do we get this plot, let us do some mathematical analysis of the signal. So for that I have selected, let yt be x of 2t. X of 2t is what we want. So I have said here, let yt be x of 2t. Okay, so now we will look at all the instants by taking different values of t. So we know original signal exists from 1 to 3. Everywhere else it is 0. So when you scale, we have to look at these values 1, 2, 3. So let me start at t is equal to 0. So when t is equal to 0, when I put here t value, what is y? Y of 0. I get y of 0. Right? And if I put t value here, 2 into 0 results into x of 0. What is x of 0? Where do I get this value? I get this value in the original signal. So what is x of 0? X of 0 is 0. And hence y of 0 becomes 0. Let me take the next time value, t is equal to 0.5. Friends, it's a CT signal. So t exists for all values of time. So I have taken a non-integer value, right? T is equal to 0.5. It's a CT signal. So 0.5 means I'm talking about this time instant. So t is equal to 0.5. So what is y? Y of 0.5. Let me put t as 0.5 here. So y of 0.5. Right, so moment I put t as 0.5, it becomes t in 2 into 0.5. So what is 2 into 0.5? X of 1. X of 2t, when I put t as 0.5, results into x of 1. Right, so what is x of 1? So where do I get this value? So for this value, I have to go into the original signal. So here is x of 1. What is the value at x of 1? The magnitude is 2. And hence, y of 0.5 becomes 2. Let me look at the next time. I'll now go for the next time. T is equal to 1. So when I put t as 1, y of 1. Put here t1. So x of 2. So y of 1 is taking a value of x of 2. That is the meaning of that. y of 1 takes a value x of 2. What is x of 2? Where do I get this value? I get this value in the original signal because here is my x signal. So x of 2. So what is the value of x of 2? What is the magnitude? So magnitude is going from 2 to 3. So definitely this is the midpoint. So what should be the magnitude? 2.5, right? And that's why at y of 1, which is taking a value of x of 2, the magnitude is 2.5. Similarly, at t is equal to 1.5. Now I am analyzing which time period? This. T is equal to 1.5. So at t is equal to 1.5, what is the value of y? Y is 1.5. When I put here 1.5, x of 2 into 1.5 is x of 3. What is the value of x of 3? I get this value in the original signal. So x of 3 is taking a magnitude of 3. Right? So you can see here. That's why y of 1.5 becomes 3. Let me talk about the next time period now. Y is 2. T is 2. So when I take y of 2, 2 into 2, x of 4. What is the value of x of 4? X of 4 is 0. There is nothing here. So the signal is 0. Now friends, if I go on increasing for other time instant, what do you observe? It's going to be x of 5, x of 6, x of 7. But we know that the original signal does not exist for any of these time period, and hence y for all these outputs is going to be 0. Now using all these y values, we'll plot the output signal. So yt is nothing but x of 2t. So I'm plotting here x of 2t means I'm indirectly plotting the y values. Right? So let me start with y of 0. So at 0, what is the magnitude? 0. So you could see here at 0, there is no signal. It means that magnitude is 0. Let me talk about y of 0.5. So at 0.5, so where is 0.5? Where is the time 0.5? Between 0 to 1. So this is definitely 0.5. So at 0.5, what is the magnitude we should sketch? The magnitude should be 2. And you could see here, we have taken at 0.5, we have taken the magnitude to be 2. At t is equal to 1, what is the magnitude? Y of 1. So it becomes 2.5. So at y of 1, it becomes 2.5. Right? So at x of 1, you could say y of 1, the magnitude is 2.5. Similarly, at y of 1.5, you could see here, I'm talking about this time instant, y of 1.5. What is the magnitude? It is 3. And y of 2, it is 0. It means that after this, the signal is going to 0. So this is how we have, with these values, we have sketched the signal x of 2t. Right? And hence how the signal looks like. Now if you compare the original signal with with the resultant new signal, how the signal looks like? The signal is a compressed signal, right? This original signal compared with the new signal, how is the signal? It is a compressed signal, right? So here the original signal was extending from 1 to 3. In the resultant output x of 2t, how is the signal? Signal just exists from 0.5 to 1.5. Can I say it is compressed with respect to time? Yes. What about the magnitudes? The signal was having a magnitude which was going from 2 to 3. Here, when the signal is compressed, the magnitude still is going from 2 to 3. So, no change in the magnitude. What changes is the time, and hence this is called as time scaling operation. No change in the magnitude. The signal is simply changing with scaling with respect to time, and hence it is called as time scaling operations. Right, so is this clear that this particular mathematical operation that we have done, is it guiding you or proving that when we do x of 2t, when a is greater than 1, my a is 2 here, we are getting a compressed signal. Right. How is the other way instead of doing all this? This is what I have told you to understand and interpret that yes, when a is greater than 1, it results into signal compression. But how could I directly obtain this without doing this particular procedure? Is now we know that if a is greater than 1, is going to result into signal compression. Right? So the direct way of achieving the final output from the input signal is simply divide the time axis by 2. So divide 1 by 2. 1 by 2 means 0.5. So you could see here the signal starts at 0.5. This particular point 2 divided by the scaling factor here, it is 2. So 2 by 2 means this particular point is appearing at 1. So at this point the magnitude was 2.5. Here when I scale it, it is appearing at 1. Now here 3 by 2. When I divide it, where is this ending point appearing? It is appearing here at 1.5. Right, so this is the another way in which you can directly obtain a compressed signal from the input signal. Right. Now I've taken again the same signal, friends, but this time we are doing the operation of t by 2. Earlier we did x of 2t. Here I am doing a next operation on the signal, which is t by 2. What is the a? What is the scaling factor here? 1 by 2. The scaling factor is 1 by 2. So as we just discussed, if a is between 0 to 1, right, it results into signal expansion, right? So we are expanding the signal by a factor of 2. Earlier we compressed by a factor of 2. Here we are expanding by a factor of 2, right? So let us analyze this. How is this particular operation resulting into signal expansion? So for that we'll again do the same thing. We'll say let yt be x of 2t. We want x of 2t, x of t by 2. So we'll say let yt be x of t by 2. Now we'll analyze this for all the time instants. So let us start at t is equal to 0. So when I take t is equal to 0 and substitute here, I get the first value of y of 0. So here with t0, it becomes x of 0. What is the value of x of 0? I'll go back in the original signal. X of 0 is 0. And that's why y of 0 becomes 0. Let me take t is equal to 1. When I put here, I get y of 1. What is the value of y of 1? With t as 1, x of 1 by 2 is x of 0.5. What is the value of x of 0.5? In the original signal, there is no value. Still it is 0. And that's why y of 1 is 0. With t is equal to 2, I get y of 2. With t2, it becomes x of 2 by 2, that is x of 1. Now do I have a value at x of 1? Yes. At x of 1, the magnitude is 2. And that's why y of 2 becomes 2. With t is equal to 3, y of 3, x of 3 by 2. So x of 3 by 2 is 1.5. Right? So what is the signal at 1.5? What is the magnitude? Here at 2 it is the midpoint. So it is 2.5 here. So at 1.5 it should be half of that. So it should be 2.25. The magnitude should be 2.25. So at y of 3 magnitude is 2.25. With the next time instant, t is equal to 4, I get y of 4. Let me calculate y of 4. So I'll put t as 4 here. X of 4 by 2, that is x of 2. So y of 4 is taking a value of x of 2. What is x of 2? X of 2 is here. The magnitude is between 2 and 3, that is it is 2.5. So at y of 4, the magnitude is 2.5. Going ahead, with the next time instant, t is equal to 5, I get y of 5. With t as 5, it becomes x of 2.5. Where is this value x of 2.5? What is this value? It is definitely between 2 and 3. So 2.5, the magnitude is between 2.5 and between 3. Right? Between these 2 points. So what should be the magnitude here? It should be 2.75. Right? Going with the next time instant, y of 6, it comes out to be 6 by 2, that is x of 3. What is the value at x of 3? X of 3 it is, here the value is 3. So x of 3 is 3, the magnitude is 3. If I now go for the next time instant, y of 7, what do you expect here? It will be x of 3.5, right? If I put here, it will be x of, what is the value at 3.5? It is 0. So all the values above 3, we know that input is going to be 0. So need not analyze the next time instant because input signal itself is 0 for all the remaining time instants. So here is what we need to stop. Now with these values, we will plot the new signal. right? We are now plotting x of t by 2. X of t by 2 is nothing but y of t. So y of 0 to y of 6 is what we'll plot here. Let us start. Y of 0 is 0. Y of 1, what is the magnitude at 1? Is still 0. Y of 2 is 2. Here is where we start. So y of 2 at this second time instant with t is equal to 2, right? The magnitude is 2. Y of 3, it is 2.25. So you could see here it is 2.20. It is slowly at y is equal to 3, it is 2.25. Y is equal to 4, it is 2.5 in between 2 and 3 here. At y of 5, it is 2.75, and at y of 6, it is reaching to 3, right? And after which the signal is 0, and hence we bring this down to 0. Right? So how is the new signal with respect to the original signal? Clearly, x of t by 2 is an expanded version of the original signal, right? It is a signal expansion. So when the scaling factor is between 0 to 1, the signal is resulting into scaling is resulting into signal expansion. When a is greater than 1, it is resulting into compression, right? So how is the signal expanded? What is the expansion factor? Is your scaling factor. Your scaling factor is 2, right? So you're expanding by a factor of 2. So simply you could see here this signal is expanded by 2. So as we discussed earlier, without doing this particular mathematical analysis, how can I obtain this particular signal directly from this? When I now know that my a value is less than 1, we know we are going to perform expansion. It is going to result into expansion. So simply multiply your time axis by the expanding factor. So 1 into 2. Now multiply the time axis by 2. So 1 into 2. So this particular starting point appears at 2. 2 into 2, 4. So you could see here this magnitude is appearing at 4. 3 into 2. So this ending point of the signal is appearing at 6. This is how simply you can directly land into signal expansion by multiplying this time axis by the scaling factor. So in the previous signal compression, divide the time axis by the scaling factor. My scaling factor is 2. So here if you divide the time axis by 2, you get the compressed signal. Whereas if your scaling factor is between 0 to 1, then we know it's going to be expansion. Simply multiply the time axis by 2, you get the expanded signal. So this is how you can do time scaling operation. Let us look for DT signals also. Right? So here is an example. Xn is given to you. How many samples are there in Xn? There are 4 samples having magnitudes 4, 2, 1 and minus 2. What are we expected to do? We are expected to find x of 3n, friends. It means that a is greater. My scaling factor is 3. A is greater than 1. It means that it should result in compression of the signal. Right? So let us understand how this signal is getting compressed. Right? So to understand this, as we are doing it for the first time, I have to make you understand I have taken a support of mathematical analysis. So we'll begin with the same way. I'll say let yn be what we desire, x of 3n. So I'll say let yn be x of 3n. Right, now the samples are from 0 to 3. How did we plot the signal from the given information? So if you remember, the first sample appears at 0. So at 0, the magnitude is 4. The next sample appears at 1. The magnitude is 2. The next sample appears at the next time instant, that is 2, whose magnitude is 1. Next, the last sample whose magnitude is minus 2. This is how we plotted from the given input signal. We have plotted the input signal xn. Now this signal xn, we are going to scale it and obtain a new signal x of 3n. So before we plot this, let us analyze how we are going to plot it by doing a mathematical analysis. So I'll say let yn be x of 3n. So I'll start with the first time instant n is equal to 0 because signal starts at 0. And that's why I'm starting with n is equal to 0. So with n is equal to 0, if I substitute here, I get y of 0. What is the value of y of 0? Y of 0 takes a value of x of 0. 3 into 0 is 0, x of 0. What is the magnitude of the signal at x of 0? So at x of 0, we see we have a sample whose magnitude is 4, and hence y of 0 takes a value 4. When n is 1, right? What is the value? Y of 1. What value y of 1 is taking? Y of 1, if I put it here, it becomes x of 3, friends. Y of 1 is taking a value of x of 3. What is the magnitude of x of 3? At x of 3, the magnitude is minus 2. So at y of 1, magnitude is minus 2. With n is equal to 2, y of 2. Y of 2 takes a value of 3 into 2, x of 6. Y of 2 is taking a value of x of 6. What is the value of x of 6? If I go into the original signal, there is no sample at 6. Signal is 0 after 3. It means that y of 2 takes a value of 0. When n is 3, y of 3, right, takes a value of x of 9. Again, as you see, there is no signal at 9, y of 3 is 0. So if I go on further doing these analysis, we definitely know that there is no sample after this, and all the magnitudes at y of 4, y at n is equal to 4, n is equal to 5, and so on, all magnitudes are going to be 0. So with this, now we'll plot the signal, right? So we are going to plot x of 3n. X of 3n is nothing but y of n, right? So let us plot it. So at 0, at n is equal to 0, what is the magnitude? We have a magnitude of 4. So at 0, we have a magnitude of 4. At 1, we have a magnitude of minus 2. So at 1, we have a magnitude of minus 2. Rest all the samples are 0. So how many samples did we finally obtain? We obtained only 2 samples, friend. Here there were 4 samples in the original signal. When we did the scaling, we obtained only 2 samples. So is it not the compression of the signal? Yes. What happened to these 2 samples? So these 2 samples are lost in the scaling process, right? That's why signal compression in DT signals results in loss of samples, right? I repeat, in DT signal compression results in loss of samples, right? We have lost these 2 samples in the process of scaling the signal, and hence signal compression results in loss of samples. This was not true for DT signals, friend, right? If I go back, right, we had done signal compression in CT signal, friends, but if I compare the original signal and the CT signal, I have not lost anything. No information is lost here. I can recover back the original CT signal, right? But in case of DT signal, that is not true. I cannot go back and obtain the samples which are lost. The samples which are lost are entirely lost, cannot be recovered in DT signals, right? So this is very important that when you're doing scaling in DT signals, and if the scaling factor is greater than 1, you are doing signal compression, and signal compression in DT signals results in loss of samples, right? So without doing this particular mathematical analysis, how can I directly obtain this particular signal from the original signal? We'll apply the same rule that we applied. What we are doing? We are scaling by a factor of 3. So divide the time base by 3. So 0 divided by 3 remains 0, and that's why this sample is reappearing in the signal compression at 0 with the similar magnitude. What about this particular sample? Now divide this particular sample is at 1. So divide the time base by 3. 1 by 3. What is the resultant times we are obtaining? It is 0.33. So you know, friends, that this is a DT signal. The base takes the base n takes only integer values. We don't plot the signals at 0.5, 0.33, 0.75, 2.5. No, the samples are appearing at 0, 1, 2, 3, only at integer values. And hence 1 by 3 results into a non-integer value and hence is discarded. That's why this sample is not appearing in the final output. When I talk about the next 2 by 3, when I divide this, where is this sample appearing? 2 by 3 is again giving me a non-integer value, right? That's why this sample is being lost. When I come to the next 3 by 3, if I divide this time base by 3, 3 by 3 is 1. So this sample appears where? This sample appears at 1. Right, with the magnitude -2, right? So whatever samples are appearing here, the magnitudes remain unchanged, right? This is how with a simple division with to the base, you can directly obtain the times compressed DT signals. Let us talk about expansion. So if you friends, I have taken the same example again, right? 4, 2, 1, -2, same signal, DT signal, but this time we are doing signal expansion. We are doing scaling by a factor of 1 by 3. My A is 1 by 3. I want x of n by 3. It means my scaling factor is 1 by 3, right? So let us once again take the support of mathematical analysis and then sketch the signal, right? Let us start with n is 0, right? So with n as 0, if I substitute here y of 0 becomes 0 by 3, that is 0, x of 0. So y of 0 takes the value of x of 0. What is the sample at x of 0? X of 0 has a sample of magnitude 4 and hence y of 0 takes a value of 4. With n is equal to 1, I get y of 1. Y of 1 is x of 1 by 3. So when 1 by 3, as we just said, x of 1 by 3, it's a non-integer value. There's nothing at 1 by 3 here and that's why undefined. Right? We don't know what is the magnitude. It is undefined. So such samples are discarded. We don't take such samples in the final output. If I take n is equal to 2, I get y of 2. Y of 2 is x of 2 by 3. So x of 2 by 3 is again a non-integer value. You don't have anything at x of 2 by 3 here. Right? So undefined, the magnitude is undefined and hence such sample is discarded. So we are discarding n is equal to 1 and n is equal to 2 samples. Now with n is equal to 3, what we get? Y of 3. Y of 3 is 3 by 3, x of 3 by 3, which becomes x of 1. What is the magnitude at x of 1 in the original signal? At x of 1 it is 2 and hence y of 3 takes a magnitude of 2. Let me talk about the next samples now. N is equal to 4, n is equal to 5. If I put n is equal to 4, it becomes x of 4 by 3, non-integer, discarded. N is equal to 5, 5 by 3, it becomes non-integer, again discarded, right? So yn is undefined for these two values. If I go for n is equal to 6, so x of 6 by 3 is x of 2. So what is the value at x of 2? X of 2 it is 1 and hence x of 6 becomes 1 and so on, right? So if n is equal to 7, 7 by 3, non-integer, discarded. N is equal to 8, 8 by 3, non-integer, discarded. N is equal to 9. If I put here n is equal to 9, what do I get? Y of 9. X of 9 by 3, x of 9 by 3 is x of 3. So x of 3 has a magnitude -2. So y of 9, the next sample appears at y of 9 whose magnitude is -2. So with all this information, if I plot the signal, so I am now plotting x of n by 3. X of n by 3 is y of n. So y of 0, at 0 the magnitude is 4. Y of 1 undefined, we discard. So 0 here, discard means there is nothing here. Y of 2 undefined, nothing here, right? Y of 2 is undefined, no sample here. Y of 3 is 2. You can see here at y of 3 it is 2. Then y of 4 undefined. Y of when n is 5, y of 5 is undefined, so it is 0 here. Y of 6 is 1. Right? Similarly, we discuss at 7 and 8, undefined. At 9, this last sample appears at 9. Right? So compare the original signal with the new signal here, friends. Can I say this, all these samples are appearing? Yes. 4, 2, 1 and minus 2. All these samples are appearing, right? But how are they now? They are appearing with larger time instant gaps. So I can say signal is being stretched or expanded. Yes. If with respect to original signal, this signal seems to be expanded. Right? Is there any loss of sample here? No. So signal expansion is not resulting in loss of samples. Loss of samples happens only if you are doing signal compression. That is also applicable only to DT signals. Right, so here there is no loss of signal, signal is expanded. So now without doing this particular mathematical analysis, how can I directly obtain the expanded signal? So follow the same thing that we just discussed. What is your scaling factor? Your scaling factor is 3. It is having a value, it is doing expansion as it is less than 1. Your A value is 1 by 3. So it means that you're going to expand the signal. So multiply your time base with the scaling factor. So 0 into 3, 0. So this particular sample appears at 0. With n is equal to 1, here 1 into 3 is 3. So this sample is appearing at 3. 2 into 3, 6. So this sample is appearing at 6. 3 into 3, 9. So this sample is appearing at 9. So this is a simple way in which you can directly obtain your expanded signal from the original signal. So what we understand now with all these 4 examples, that if your scaling factor is greater than 1, that is A is greater than 1, it results into signal compression. And if A is less than 1, that is between 0 to 1, it results into signal expansion. So if you simply remember this, you can easily solve the problems on time scaling. Now let us do examples on time scaling operations, right? Now a signal is given to you, friends. Signal, how is it defined? A CT signal is defined for you. X of t is equal to 2t for the time region between minus 1 to 3 and it is 0 everywhere else. And we are going to perform 2 operations on it, x of 3t and x of t by 2. So with this particular given problem, how would we solve the given numerical, right? So what is the very step 1 that you need to do, friends? Since signal is not sketched for you, you need to sketch the given signal from the given mathematical equation of the signal, right? So how do we do that? So for that, look at the given time over which the signal exists. So signal exists from what range? Signal exists from minus 1 to 3. So the very first thing that you have to do is mark those time instants on the axis. So mark the signals as minus 1, 0, 1, 2, 3. Mark these points because signal is going to exist only at these points. Everywhere else it is 0. So signal is going to exist only for these time instants. What is the very first step that you will do? When you are given a mathematical equation, look at the time instants, okay, and mark those time instants. Now let us start to plot. So what is the very first time instant? Minus 1. So if I take t as minus 1, what is the magnitude at minus 1? So put t as minus 1 here. So 2 into minus 1 is minus 2. So what do we understand? At t is equal to minus 1, the magnitude is minus 2. So I'll plot that now. So at t is equal to minus 1, the magnitude is minus 2. Here it is minus 2. Minus is missed. So minus 2, right? So at t is equal to minus 1, the magnitude is minus 2. Take the next time instant, t is equal to 0. When I put t as 0, x of t becomes 0. So at 0, the magnitude is 0. When I take t as 1, the magnitude is 2. So at 1, the magnitude is 2. When t is taking value of 2, magnitude is 4. So at 2, the magnitude is 4. When t takes a value 3, magnitude is 2 into 3, that is 6. So at 3, the magnitude is 6. So if I now simply join these points, right, what magnitudes we had got? -2, 0, 2, 4, 6. So simply join these points, and this is the line that you get when you join it. And what we know, outside this the signal is 0. So simply bring the signal down to 0. Right? So bring it to 0. Right? So this is how you get the signal. Right. Now once we plot the input signal, what is the next thing that we need to do now? Now we focus on what is desired. We are expected to do two operations on the signal. Right? The first operation, let us do the first thing. X of 3t. So what is the scaling factor here? The scaling factor is 3. So A is greater than 1. It means that it is going to result into signal compression. So we are now going to, in the first numerical, we are going to do signal compression. Right? So how to do that? So I've told you, right? Look at your scaling factor. Your scaling factor is 3. So simply divide your time base by 3 and mark the new points where your signal is going to be reappearing. So let us start. So -1 by 3, right? Divide this by 3. It's going to compress. Compression means divide. When you're going to expand, multiply. That is the difference, right? When you're, because x of 3t means, now we understand it's going to be compression of the signal. So compression means I should divide the time axis. So my signal starts at -1. So -1 by 3. So this particular point, once I scale, where is it going to appear? It's going to appear at -1 by 3. So you could see here, friends, I've started at -1 by 3. At -1 by 3, the magnitude should be -2. Go to the next point, 0. 0 by 3, 0. 0 point doesn't change. So at 0, signal crosses 0. Magnitude is 0. Now where is this point going to appear? 1 by 3. Right? This particular point will appear at 1 by 3. This particular point will appear at 2 by 3. And where will this end terminating point of the signal appear at? 3 by 3. It means that this particular terminating point having a magnitude of 6 is going to appear at 1. So if you simply go to 1, magnitude should be 6. So now you know the starting point, you know the ending point, where the signal is going to appear. Simply join the magnitudes, and if you join it, this is how you see is the compressed signal. What is essential for you to understand is the starting and the terminating points when the signal will be compressed. So starting point is -1 by 3. Terminating point is 1. 3 by 3 is 1. Right? So starts at -1 by 3, terminates at 1. And now in these 2 points, simply draw the signal. Right? So it will naturally look as a compressed signal. Right? So the x of 3t is the compressed signal. Let us move to the next. Now we have been asked to do x of t by 2. So your scaling factor is A is 1 by 2. So where A is between 0 to 1, we clearly understand it results into signal expansion. So I am now going to do signal expansion. How to do signal expansion? So multiply the time axis by the scaling factor. So scaling factor is 2 here. So multiply by 2. Expansion means I have to multiply. Compression means I am going to divide. So let us start. So this particular point, -1 into 2, where is the starting point of the signal? The starting point, this particular starting point, when multiplied by the scaling factor 2, will appear at -2. So you can see here, signal starts at -2 with a magnitude -2. 0 into 2, 0. So this particular point remains at 0. Magnitude here is 0. This particular point, 1 into 2, will appear at 2. So this particular point appears at 2. This particular point appears at 4. I am interested at the terminating point. Right? Terminating point has a magnitude 6. Right? So multiply this particular time axis by the scaling factor. Scaling factor is 2. So 3 into 2, 6. So where we are going to terminate the signal, friends? We are going to terminate the signal at 6. So you could see here, at 6, the magnitude is 6. So we know the starting point, we know the ending point where the signal is going to end. Simply draw the magnitude, mention the magnitude at the starting point, mention the magnitude at the ending point, simply connect the point, you will automatically get the expanded version of the signal. Right? So x of t by 2 has resulted in signal expansion. Look at the magnitude or the shape of the signal. The magnitude or the shape of the signal remains unchanged. Magnitude doesn't change, friends. Scaling results into changing the scale of the time axis. Right? So t by 2 has resulted into signal expansion. 3t has resulted into signal compression. Right? This is way you will solve the numericals on scaling. Now we'll take an example of DT signal. Right? So a DT signal is given to you here. This is the equation of the DT signal, with which you have to first of all sketch your DT signal and then do the operations which have been asked to you. So what is the equation given to you? Your signal xn is 1 minus n for the time period between minus 3 to 2. So your signal is from minus 3 to minus 2, right? And it is 0 elsewhere. What are you being asked to do? You are being asked to do x of n by 3 and x of 2n. So before we plot the resultant outputs, we'll first of all sketch the input signal, right? So let us do it together. So xn, right? What do we understand? Xn is present only for what time period? It is present for a time period between minus 3 to 2. So we'll mark only those time instants first. We'll mark those minus 3, minus 2, minus 1, 0, 1 and 2. We'll mark only these time instants first. Now we'll start to plot the signal. Right, so let us start with the first time instant. Minus 3. The moment I put here minus 3, what is the resultant magnitude? 1 plus 3. So xn is having a magnitude of 4 when n takes a value minus 3. So at minus 3 it is 4. When n takes a value minus 2, 1 plus 2, the magnitude is 3. When n takes a value minus 1, at minus 1 what is the magnitude here? 1 plus 1, it becomes 2. So at minus 1 the magnitude is 2. When n takes a value 0, what is the magnitude? Resultant magnitude with n 0, it is 1. So when n is 0, the magnitude is 1. When n takes a value 1, 1 minus 1 becomes 0. So at 1, there is no sample here. As you see, it is 0. When n takes a last value 2, right? 1 minus 2, it becomes minus 1. So when n takes a value 2, the resultant magnitude is minus 1. Everywhere else it is 0. So did not think about rest of the samples. They are 0. So your signal is present from time instants minus 3 to plus 2. So these are the input signals. Right? With these input signals, now we will obtain the desired, we'll do the operations on these input signals. So what is the first operation we'll be doing? We'll be doing x of n by 3. This is what we are expected to find. What is the scaling factor? Scaling factor is 1 by 3, right? So with scaling factor 1 by 3, we understand it's going to be resulting into signal expansion. So we are going to expand the signal. We are expanding by what factor? What is the factor by which you are expanding the signal? By a factor of 3. Right? So it is 3 here. We are expanding the signal by a factor of 3. So how do I obtain the signal? Simply multiply the time base by 3. Right, so where will this sample appear? Minus 3 into 3 means minus 9. So you expect that at minus 9, the magnitude is 4. Right, where will this sample appear? Minus 2 into 3, minus 6. So this sample will appear at minus 6. So magnitude is 3. What about samples at minus 8 and 7? No samples there. So it means that it is 0. Right? Now look at the third sample. Multiply it with the scaling factor. Minus 1 into 3. So where will this sample appear? At minus 3. You could see here at minus 3, the magnitude is 2. 0, sample at 0 remains at 0. So it is 0 here. This is 0. 1 into 3, 0. It remains 0. Right? What about 2? 3 into 2, 6. So this sample is appearing at 6. Could see here. Right? So this particular sample is appearing at 6, whose magnitude is -1. So with respect to original signal, your new signal x of n by 3 is an expanded signal. Right? Where there are no samples, the magnitude is 0. That should be clear. And where there are no samples, it means that these samples are 0. Now let us go for the next. What has been asked to you? In the next case, you have been asked to do x of 2n. You have to find this operation x of 2n. So x of 2n means it's a scaling. What is the scaling factor? Scaling factor is 2. A is greater than 1. It means that it is going to result into signal compression. By what amount are you compressing the signal here? You are compressing the signal by a factor of 2. Right? So compression means you should divide the base by 2 to obtain the compressed signal. Right? So let us start. So minus 3 by 2. So it is resulting into a non-integer value. So this particular sample will not appear in the resultant signal, because where is it reappearing? Minus 3 by 2. It is appearing at minus 1.5. Minus 1.5 is a non-integer value. So signal is undefined there, and that's why it does not appear, because n takes only integer values, and that's why this signal does not appear here. What about this? Minus 2 by 2. So this sample appears at minus 1. Right? So you could see here. The sample having a magnitude 3 is appearing at minus 1. What about this sample? Minus 1 by 2. Non-integer. Base is becoming non-integer. This will be discarded. This will not appear. Right? What about 0? Sample at 0 remains at 0. You could see here. This sample appears as it is. 1 by 2, this sample will be discarded. As it is 0. 2 by 2, divide this base by 2. So 2 by 2 means this sample is appearing at 1. 1 is an integer value, so it appears. So this sample having a magnitude of minus 1 is appearing at 1. So how many samples you had in the input, friends? 1, 2, 3, 4, 5. This was 0. So 5. So and how many appeared when you compress the signal? Only 3. So it's a loss of samples, right? So when you compress DT signal, it results into loss of samples, right? So this is the way you do scaling on the signals. Now we move on to the next category of signal operations, in which we'll combine all the three operations, friends. So we'll be combining time reversal, time shifting and time scaling, all the three, and perform operation on the signals. Right? So if you have been given such a problem, how would you proceed with sketching of such signals? Right? So what should be a step number 1 in that case? Step number 1, you identify what all operations are present in the input signal. Step number 2, if there is a time shifting, then time shifting operation has the highest priority. This is what is very, very important, because we have three operations: time shifting, time reversal and time scaling. Right? So if all the three are present, then which operation should be performed first? It is always the time shifting operation that should be performed first. This is the rule. This is what you should note down very properly. We should always perform time shifting operation first. Then there is no priority among time reversal and scaling. After you perform time shifting, you can go either of any one of these. Either you go for time reversal or you go for scaling. Any one would be fine. So with these set of rules, we will try to solve certain problems. So you have been given a signal yt. Yt is already given to you. It's a sketch signal. Yt extends from -2 to 2, right? And you have been asked to do this particular operation on yt. So what is the operation? Y of -2t minus 3. This is what you are expected to find and sketch. What did the steps say? Identify the signal operations. So let us first identify what are the operations present in this signal. So there is t minus 3. So t minus 3 indicates shifting. There is 2t involved here. So 2t indicates scaling. And the moment there is a minus sign associated with t, it indicates reversal. This is how you identify the operations. I repeat, t minus 3, there is a t minus 3 here, t minus 3, t plus t naught or t minus t naught, if you remember, indicates shifting. So there is shifting here. There is y of at, right? So you are multiplying something to time, so that is scaling. This is how you identify there is a scaling here. And a minus sign with t associated with t indicates there is reversal. So there are all the three operations hidden in this, right? So how would you proceed? So what we just discussed in step number 2, perform time shifting operation first. So we'll perform in step number 1, we'll perform time shifting. So I'll be performing time shifting. What signal will I get when I'll perform time shifting? I'll be shifting it by a factor of 3. So what signal will I get? Y of t minus 3. This is what I'll be sketching first. Understand? Here is t minus 3. So I'll be obtaining y of t minus 3. Right. Now if you remember, if you have revised, then you understand that it's a shifting. It's a t minus t naught signal. It is going to be signal delayed. Signal delayed by 3 units. Delayed signals are shifted to right hand side. So you can see this entire signal we have shifted to right hand side by 3 units. How did we plot this? So start with the extreme end. Shifted 3 units to the left. So 3 minus 2 shifted 3 units to the, 3 units to the right. Minus 2 shifted 3 units to the right. Where will this particular point appear when it is shifted by 3 units? Definitely this is 1, 2 and 3. Third point. So minus 2 will appear at 1. Right? So minus 2 appears at 1. What about the ending point? Shifted by 3 units will appear at 5. So starting point is 1, ending point is 5. So in between this you draw your signal. This is how you get your shifted signal. Mark the starting and the ending points of the shifted signal, right? So this particular point appears at 1 when you shift it by 3 units to the right. This particular point shifted by 3 units to the right appears at 5. So once you obtain the starting and the ending point, what you need to do is simply sketch the signal in between this new time period. You get your shifted signal. This is your step number 1. Now what you do in step number 2? You're going to do the next operation, that is now 2 operations are remaining, friends. Either you go for scaling or you go for reversal. So here I have selected scaling. There is no priority to both of this. This is having highest priority. Right? That's why we did time scaling. Right? There is no priority now to the remaining operations. You can do any of them. So I have opted for, in step number 2, I am going to do scaling. Right? So I am going to scale this signal. What is the scaling factor? Y of 2t. So A is 2 here. A is greater than 1. Right? So it's going to result into signal compression. So we are going to compress the signal. Now which signal are you going to compress, friends? Not the original. You're going to compress the shifted signal, right? So you're going to do operation on this, not on the original signal, right? So we are going to compress this signal by a factor of 2. So how did we discuss it? So when we compress, we divide the time base by 2. So mark the starting and ending point. So this particular point, when divided by 2, where it will appear? At 0.5. 1 by 2 appears at 0.5. So starting point is 0.5. Where is the ending point? 5 divided by 2. So ending point is 2.5. So signal terminates at 2.5. It means that signal is going to exist from 0.5 to 2.5. So I need to draw my signal in between these new time instants. Right? So identify where is this particular point. Where is this particular point? At 2. So 2 divided by 2 is 1. So this transition, where is going to appear? This transition is going to appear at 1. Rest, the signal remains at 2. So simply draw your signal at the new identified time instance. You get your time compressed signal. Right? So this is step number 2. Now what we do? Now we go to the next. And what do we call this signal, friends? Yeah, this is important. What do we call this signal? earlier it was y of t minus 3. We did scaling on this. So the new name of the signal is y of 2t minus 3. Right? You did scaling on this. Scaled by a factor of 2. So the name of the signal is y of 2t minus 3. Now what remained? What remained is putting a minus sign to t. Applying a minus sign to t means I have to do reversal. I have to reverse this signal now. So what is doing reversal? Doing reversal means obtaining the mirror image of this. So in the last lecture we had discussed how to do reversal. So in step number 3 we will be doing reversal. How to do reversal is simply change the time axis. So plus 0.5 should appear at minus 0.5. Plus 2.5 will appear at minus 2.5. Right? So you simply change the magnitude of your time. If it is positive, make it negative. If it is negative, make it positive. So magnitude doesn't change, friends. Magnitude is 1 and 2. Magnitude is not changing in any of the cases. What changes is the time. Right? So how to do time reversal? So plot the signal with respect to the new time axis with time reversed. So what is the starting point here? Plus 0.5. So whatever is at plus 0.5, when I change the sign, will appear at minus 0.5. So you could see at plus 0.5 the magnitude was 1. At minus 0.5 the magnitude is at 1. Where will this point appear? What is the magnitude? Magnitude is 2.5. Time reversed, change the sign of the time, it is at minus 2.5. So this particular point will appear at minus 2.5. Now you sketch your signal at the new identified time instance. Right? Whatever you get is your time reversed signal. Right? So this is what was expected for you to find y of minus 2t minus 3, and this is what you have obtained here. This is your resultant signal. So following these steps you get your resultant signals. Right. See, what I have done, I have taken the same example here, friends. This is the next example, but I have done the same thing, y of minus 2t minus 3. What I wanted to show you here is that in the earlier case, in step number 2, I did time scaling first and then I did time reversal. I want to prove you that because there is no priority to any of these, if you do any of these operations, right, the signal results remains the same. So what we did here, this was the input signal. Step 1 is you need to do time shifting first. We did time shifting of this signal by 3 units like the earlier. Now in step number 2, instead of doing scaling, we did reversal. Right? So this signal we reverse. The same problem we are resolving again. Right? The same problem I am solving again by interchanging reversal and scaling operation. Right? I want to see whether I get the same signal. So what I did, given my problem, I did time shifting first. So we shifted the signal the way we did it earlier. Now we did reversal of the time shifted signal. So I reversed this. How did we reverse? So change the sign. So plus 1, whatever is at plus 1 will appear at minus 1. So at plus 1 the magnitude is 1. At minus 1 magnitude is 1. At plus 5 the magnitude is 2. At minus 5 the magnitude is 2. At plus 2 the signal changes from 1 to 2. At minus 2 the signal changes from 1 to 2. So simply if you join the points you get the time reverse signal, right? You get your time reverse signal. Now step number 3, I did scaling on this. So what is the scaling factor? 2. What is the signal you obtained here? Y of, earlier it was y of t minus 3. We did reversal. The moment you do reversal, what is the name of the signal? You need to put a minus sign there to t. So the new signal that we did here is named y of minus t minus 3. Now we are going to do scaling. Scaling is by a factor of 2. So how would you name the signal? Append the scaling factor to your t. So what is the name of the signal? The signal was earlier minus t minus 3. When scaled, the name of the signal becomes y of minus 2t minus 3. Right? So now we are going to scale this time reverse signal. What is the scaling factor? 2. So divide the time base by 2. So where this point appears, minus 5 by 2 appears at minus 2.5. Minus 1 appears at 0.5. So you got your starting and ending point. So signal exists from minus 2.5 to 0.5. And in this new time region, you draw the scale, you draw your magnitudes of the signal, you get your time scaled signal. Now you compare this signal with the original, with the earlier problem. So I'll go to the previous slide where we did scaling first and we did reversal. This was the signal we obtained, minus 2.5 to minus 0.5, right? Whereas when we did reversal and then did scaling, we got the same result. So it's very clear that if we do reversal first and then followed by scaling, or scaling first then followed by reversal, we get the same signal, right? Signal doesn't change, right? So it's very clear that we should always do time shifting first, then do time reversal or scaling, any of because these two have no priority. What is important is giving highest priority to time shifting. Then you perform reversal or you perform scaling, any operation, the signal results the same. Okay, one DT signal will look and then we'll stop. Right, so you have been given a DT signal here and then you have been asked to perform, you have been asked to find this signal, friend, x of minus n by 2 into un. So input signal consists of how many samples? Samples from minus 2 to plus 3. You have been given a DT signal which exists from minus 2 to plus 3, having magnitudes which are changing from 3, minus 2, 4, 2, 1 and 5. Whereas you have been while you have been asked to find x of minus n by 2. So what was step number 1 that we just discussed? Identify the operations in the signal. What are the operations here? There are two operations. There is no shifting here now. There are two operations. There is a minus sign associated with n. So if there is a minus sign associated, what do we understand? It's a time reversal, right? And n by 2, it means that there is a scaling. So there are two operations we identified. One is reversal and one is scaling. And then we have to multiply the resultant signal by unit step signal. So we'll first of all do step number 1. Let us do scaling, because we can do reversal also, we can do scaling also. Both have equal priority. So let us choose one. So here I have selected time scaling operation. So we are doing what? We are now obtaining x of n by 2. The scaling factor A is 1 by 2. It means that it is going to be signal expansion. So signal expansion means simply multiply your base by the scaling factor. The scaling factor is 2. So multiply the base by 2 to obtain the expanded signal. So minus 2 into 2, it means that this particular sample will appear at minus 4. So at minus 4, the magnitude is 3. Where will this sample appear? Minus 1 into 2. So this sample appears at minus 2. Magnitude minus 2. Sample at 0 remains at 0. 0 into 2, 0. It remains at 0. This particular sample will appear at 1 into 2 at 2. So this particular sample of magnitude 2 is appearing at 2. 2 into 2, 4. This sample is appearing at 4. This sample at 3 into 2 is appearing at 6. In between, no samples means the magnitude is 0 at these instants. So this is step number 1. Now what we'll do? Now we have to do reversal, right? So we have to do reversal of what? We have to reversal of the step number 1 signal, right? So here we'll do reversal of step number 1, that is the scaled signal we will reverse. So what is the name of the signal? The moment we do reversal, I have to append a minus sign to the base. So it becomes x of minus n by 2. What I am now plotting is x of minus n by 2. What we discussed how to do reversal? Reversal means simply fold the signal about the y-axis. Let us start. So this sample in the original signal is at minus 4. This has to be time reversed. Where it will go? Change the sign of the base. So minus 4 sample will appear at plus 4. So this sample is appearing at plus 4. Look at this sample. This is at minus 2, will appear at plus 2. Magnitude is not changed, friends. Magnitude is same. Simply change the time. right? So this sample which is at -2 appears at +2 when I do reversal. Sample at 0 remains at 0. Here the sample is at +2 will appear at -2. Magnitude is +2, magnitude remains the same. So sample at +2 is appearing at -2. Sample at +4 is appearing at -4. Sample at +6 is appearing at -6. So this is how you obtain your time reversing. The rest of the samples are 0. Did not think about it. So this is your time reverse signal. So what all we have done by now from the given problem? From the given problem, we have obtained this part. We obtained x of minus n by 2. What is the next step we have to still to do? We have to obtain, we have to multiply this signal by un. Now what is un, friends? Un is unit step signal, as we had discussed in lecture number 2. These are the basic signals, right? They are predefined, they are fixed. So how is your unit step signal, friends? Unit step signal has samples from 1 to infinity and all the magnitudes are 1. Could see here all the magnitudes are 1. Right, now we are going to take the product of x of n minus 2 with un. So I'm going to multiply these two. So product means what do I get? When I take the product x of n minus 2 with un, what is the product we'll get? This signal un is 0 on the left hand side. There is no samples here. Right? It's a complete right-handed signal. UN is a right-handed signal. So there are no samples on the left-hand side. So when you no sample means it is 0 here. So if you multiply any samples which are there on the left-hand side with the samples of UN on the left-hand side, the resultant will be 0. Because -2 with a sample at -2, there is no sample here, means it's a 0. So -2 with a sample at -2 will result into 0. -6 multiplied with a sample at -6 here in UN, as there is no sample here, is 0. So it's a right-handed signal. So always remember, UN is a right-handed signal. When you multiply any signal with UN, indirectly you are making your signal to be a right-handed signal. So let us multiply now. So 0, the magnitude is 4 here. At 0, the magnitude is 4. What is magnitude here? All unit step signals have magnitude 1. So sample at 0 with magnitude 4 is appearing here. There is nothing here. 0 into 1 is 0. Then 2, sample at 2 multiplied with sample at 2. Right? Magnitude is 1. Magnitude is -2. 1 into -2, -2. So at 2, the magnitude is -2. At 3, it is 0. At 4, right, it is 1 here again, dot 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 means the signal is going to infinity, right? So at 4, magnitude 3 into 1, it remains 3. So this is your final result which has been asked here. So this is how you do signal operations, combining all the signal transformations.